A very good morning to all. Knowledge has power. It controls access to opportunity and advancement. I, Namrata Dikruz, Executive Member of IEEE Mysore Subsection, take this privilege in welcoming you all for the second day of first edition of the flagship International Conference Series of IEEE Mysore Subsection, IEEE MysuruCon 2021, hosted by Nafis College of Engineering, Hassan. I extend a hearty welcome to the resource person, Dr. Amir H. Gandomi, Professor, University of Technology, Sydney, Australia. I extend a hearty welcome to you, sir.
Thank you.
I extend a warm welcome to all the organizers and participants for this session. I now would like to introduce the resource person for the session. Dr. Amir is a professor of data science and a fellow of ARC Discovery Early Career Researcher Award at the University of Technology, Sydney. Professor Gandomi has published over 200 journal papers and 7 books, which collectively have been cited 20,869 times. He has been named as one of the most influential scientific mind and highly cited researcher for 4 consecutive years. He also ranked 18th in GP bibliography among more than 12,000 researchers. He has served as associate editor, and guest editor in several prestigious journals. His research interests are global optimization and big data analytics using machine learning and evolutionary computation in particular. I extend a hearty welcome to you, sir. I now request you to deliver the keynote address. Over to you, sir.
Thank you so much for the nice introduction. Okay, the share button is active right now. Hold on. Okay. Hold on. Could you see the full screen?
Yes, sir, it's visible, sir.
Okay. Hello again, everybody. This is Amir Gandomi. I'm a professor at the University of Technology, Sydney, and my expertise is machine learning, data analytics, and evolutionary computation in particular. I have a strong background in engineering, and today my conversation is also focused on evolutionary intelligence in engineering computation, which I call it evolutionary engineering computation. And now it's an era of big data, machine learning, evolutionary computation. So I think it would be very helpful for engineers who would like to use advanced AI and machine learning in action. I should again thank MysuruCon 2021 for having me in this event, and also Professor Paramashachari for inviting me. Thank you. So before going to the technical content, I would like to briefly talk about evolutionary philosophy. So speaking of evolution, we should go back to the evolution philosophy, which came from Rumi, also known as Maulana. Rumi was the 13th century Persian poet and philosopher from Greater Khorasan. Rumi believed in evolution in some sort of Darwinian sense. this presentation has two main parts, and I mainly focus on the first part because I think we don't have enough time to go to the all topics. So in the first part, I will discuss how evolutionary computation and genetic programming in particular can be used for analyzing and extracting information from the engineering data, and also build explicit model for engineering problems. And in the second part, I will focus on how optimization, evolutionary computation can be used for optimization of engineering system, particularly engineering design. So first, evolutionary computation for data analytics. So there are so many predictive data analytics tools, such as, and we can generally categorize them to two classes: AI methods such as neural network, fuzzy logic, support vector, and genetic programming, and statistics. And the method that I'm going to talk about is genetic programming, which is a subset of artificial intelligence. So generally in data mining, we need to make two selections. First, we should select the best features, and then we need to select the best model. So after pre-processing, we usually try to come up with the best features, and then try different methods. For example, this study, you can see we tried several different methods. Most of them didn't work, but eventually one method called XGBoost could provide us reliable prediction with about 92% AUC. So in 18th century, Charles Darwin proposed the theory of evolution in his book called The Origin of Species. And following the Darwinian natural selection, genetic programming create programs in order to find relationships between inputs and outputs. And like any other evolutionary process, it has iterations, which we call generation, as you can see. We have selection, crossover, and mutation, and this process does iteratively until we met our criteria. Uh, like life tree, genetic programming also have a tree like structures. We have terminal node, which are the end of the each leaves, and we have other nodes such as functional node and root nodes, and these nodes could be mathematical operators, variable or constant values. So now two offsprings can be made from two parents. You can see a simple example here, which shows two children which have their parents' features, and mutation with some random changes. We can also make some mutation in the solutions. But the main question here is why genetic programming? There are several other techniques are out there, and some of them are very well known, such as a neural network or support vector machine, regression, etc. So there are some reasons that I listed here, but the first one is the most important one. Genetic programming doesn't need predefined structure. Actually, it can also find the structures via evolution. So when we have any system that a structure is not determined, genetic programming can be applied in order to find that structure. So, for example, for predictive analytics, when we don't know what would be the shape of our model or equations, genetic programming can find that structures. In any other methods such as neural network or a regression or support vector machine, we have the structure. We have the structure and we solve, actually we optimize some of the coefficient or find some of, uh, uh, try to find some of the best kernel function, etc. But genetic programming does these selections via evolution. The other thing is it doesn't need predefined structures, and also it can model behavior without prior assumption. And another important things in the era of explainability is that genetic programming model is relatively short and simple in compared with complex models such as neural network model or some of the machine learning model. It's very useful. We usually can have a very simple formula or simple structure, and it's usually very easy to interpret. And as I mentioned, genetic programming can select the features inherently, which is one of the steps that we need to do in our selections. And also, it genetic programming already applied to several complex engineering problems. For example, NASA used genetic programming long time ago for designing their communication antenna. They wanted to find the best antenna structures, and you can see it here. Uh, the solution that GP found was much better than the solutions that engineering came up with, and it happens with by training this system using evolution. The other difference of genetic programming with other machine learning is that it's a population-based algorithm. So most of machine learning methods are trajectory-based algorithm. They start from one single solution and they try to optimize that solution. So they have a higher chance to trap in local optima. But genetic programming is a population-based algorithm. We can easily parallelize the system, and now in the era of cloud computing and distributed system, it could be very beneficial for us. So right now, actually, for any big data problem or large scale problem, we try to use parallel processing or cloud computing. So let's start the first example. For the first example, I selected this case study. So this is a very complex structural system. So if you are a structural engineer, you are familiar with CBF system, as a concentrically braced frame system, which is the most popular method, structural system, at least in the US, as long as I know. But we try, this system is more complex than CBF. It's a self-centering, which has some special elements such as these PT bars or energy dissipations element or adjacent column, etc. And we want to predict the roof drift of maximum roof drift of this structure under earthquake. And earthquake itself is a very stochastic process. I've shown one of the earthquake records here. You can see maximum roof drift happen here. So it shows how stochastic an earthquake is. So in order to build a model for predicting the maximum roof drift, we need to look at two categories of variables. First, a structural design variables such as geometrical or mechanical parameters of the system, and also intensity measures of earthquake. So when I look at the literature, there are more than 30 plus intensity measures out there, but I selected the most popular 14 intensity measures. And for prototype structure, I use an office building designed for a stiff soil site in LA, California. And this is the SCCBF system that I'm going to study. And I consider 3 elevations: 4-story, 6-story, and 8-story buildings. And because the system is highly nonlinear, we need to do nonlinear dynamic analysis. And we applied, actually, we designed 75 different structures, and we applied 170 earthquake in total. And for intensity measures, there was one big question: which intensity measures? There are still a lot of intensity measures out there. So what I did is actually one of the simplest way is looking at the correlation coefficient. Probably you are familiar with the correlation coefficient, or R. But correlation coefficient only represent the linear relationship between 2 sets of data. So what I did here is I modified correlation coefficient formula, and I came up with the evolutionary correlation coefficient, as you can see it here. This is the evolutionary correlation coefficient. And by using that, I try to also model nonlinear relationship between 2 sets of data. So this is the correlation coefficient between each intensity measures and output. You can see it in this column. And what I did here is modified correlation coefficient using genetic programming. And now this is the evolutionary correlation coefficient. And in this column, I presented the improvement happen when we apply evolutionary coefficient. So you can see in some cases we have more than 300% improvement, or some cases 200% improvement. So it shows how this evolutionary correlation coefficient can be useful for nonlinear system. So eventually I selected 3 intensity measures. And in genetic programming, we usually build try to come up with the Pareto front, these green solutions. And then we select one which has enough accuracy. This y-axis is accuracy, x-axis is complexity. And it doesn't have a very high complexity. So a solution usually comes, a final solution usually selected from this area. And these are the final mathematical formula for such a complex problem. You can see we come up with a very, very simple mathematical formula in order to predict roof drift of peak roof drift of SCCBF system using genetic programming. And these are final prediction result. You can see we have very high correlation coefficient. And the next case study that it's very popular in engineering is inverse analysis. So we usually in engineering do forward analysis. Yes, we apply input into the system and it gives us output. But what happens when we have input and output, but we don't have the system parameters? So this is called inverse analysis. I quickly show one framework. Actually, it is proposed by Professor Qabushi at UIUC. He proposed running 2 parallel finite elements, one of them force control, the other one is displacement control, and we come up with a database of stress and strain. and then we start training a neural network model. And this process plays in a loop, so eventually a neural network is converged. So what I saw here is, okay, we have an unknown material, we define a neural network model, but where we can go from here? There is very difficult to use this model in engineering and as a user-defined material in uh, general purpose softwares, final element software such as ANSYS and Abacus. So what I did is I simply replaced neural network with genetic programming. So after doing that, I could simply translate a genetic program to a simple mathematical formula. So eventually I came up with this. So now this can be used for developing a constitutive material model. And in engineering, we also use it for defining Jacobian matrix. So this is the uh, case study, cantilever beam applied to forces at the end, and this is the force displacement curve. This is Professor Gabushi's result. This is the genetic program translated to uh, uh, mathematical formula, and then this is the prediction result. This is the reference model, and this is the genetic programming model. You can see they are very well matched. And then I wrote that material constitutive model into Abacus software. And you can see how genetic programming based model is close to the reference model. And I applied for some other problems such as soil or aortic modeling. And there are several other case studies, for example, for MOOC performance, when signal are recorded using a head scanner from a student, you can see how genetic programming could outperform others. Or for Airfoil self-noise prediction, you can see how genetic programming outperform others. And we use genetic programming for time series forecasting of COVID. This is the results for India. And we applied for some other countries. And I also proposed some genetic programming approaches. For example, this approach that I call it multi-stage genetic programming. When I try to decompose the errors based on each dimension. So each variable used separately to make the prediction. And eventually we have a interaction function, which consider interaction between variables. And this is the result for that one. You can see MSGP, my approach could are very competitive with these three well-known techniques. And with considering interaction, it's almost perfect for this soil liquefaction modeling problem, which is a very challenging problem in engineering. And this approach very interesting for big data, because now instead of dealing with the n-dimensional model, we deal with n one-dimensional model. So we compare multi-stage genetic programming with regular genetic programming. It is a genetic programming uh, error reduction curve, and now this is the multi-stage genetic programming. You can see how quickly it can uh, reduce the error. And evolutionary computation are also widely used in the literature for optimization. We generally have two classes, mathematical and nature-inspired or evolutionary. They use other sources of information such as evolution, swarm, or annealing. There are several methods out there, and I've listed some here. If you are interested, email me and I can share the code with you, which have been very successful in the recent years. And there are some some case studies, such as we applied evolutionary computation for very large scale structures, such as these towers. You can see we applied P3 algorithm. We got a very good result in compared with two state-of-the-art methods. Or another good application for evolutionary computation is multi-objective or many-objective evolution optimization problem. So this is the very popular approach for this type of problem. And in one of our studies published recently, we compared these three problems up to 10 objectives, and we applied 18 evolutionary many objective algorithm for solving these problems. And finally, I should say nature-inspired algorithms are derivative-free, global. They have some disadvantages, but they are very flexible. And if you are an engineer and embed your knowledge into the system, you can significantly improve the performances of this algorithm. I think I only have a couple of minutes, and I would really like to answer your questions. So eventually I can conclude it's better not to use this algorithm blindly. Try to narrow down and find the best algorithm for your problems. And you can consult with the computer scientists or engineers who are expert in this area in evolutionary computation, and they can guide you. For example, if you have a multimodal problems, for example, Firefly algorithm could be one of the good choices. Or if you have a discrete optimization problem, interior search algorithm could be a good one, and so on and so forth. Thank you so much for your attention, and I would be happy to answer if you have any questions.
I request the participants to please ask your queries.
Professor, thank you. Kishore
Of
sir,
course.
any queries?
Yeah, thank you. Thank you, the Professor Amir. We also see that Newtonian classical gravitational algorithms were also a source of inspiration for some of the classification algorithms, and I have seen some of the data simplification based on Newtonian gravity. Could you just throw some light if you have also looked at the gravitational aspects?
What do you mean? Do you mean physics-based using Newtonian physics as a source of inspiration to develop a classification algorithm or optimization algorithm?
Yes, for instance, a force vector can be, say, the COVID-19 can be treated as a force vector, and all the acceleration and other mass. So we can derive different mass and accelerations as different continents, and impact of that on the worldwide. I mean, that way, that's gravity inspired mathematical modeling.
So Newtonian mechanics it's a source of inspiration in evolutionary computation. Also, there are some algorithm called gravitational search algorithm, I think called GSA, or there are some other algorithm like gravitational force algorithm or some methods like this. And I think you can use this model for any other problems, as you mentioned, like COVID and its distribution around the world. But I'm not very familiar with the topic, so I think I'm not the best person to answer these questions. But generally, I should say, if you have, so what this evolutionary computation says is, besides classical approaches like derivative based error reduction or derivative based optimization, you can use other source of information. You can use evolution, you can use swarm behavior, you can use annealing, you can use gravitational forces, and all other model out there could be somehow used in order to solve real world optimization problem, because this is a way of nature that solving these problems. Yes, that's how these how nature works. And they can these evolutionary computation says you can borrow those inspiration and use it for some engineering or as you said, medical or COVID prevention problem.
Thank you. And one more, you modeled a multi-storied complex. In that model, it can be like one conglomerate, one ensemble. If we have a parallel ensemble sitting next to it with something similar to a digital replica, and if you can create a relation between the running model and an ideal model, it helps us in solving some of the challenges of as you mentioned about earthquake and some emergencies. Like we can actually model some things like La Palma, a volcano which is active for quite some time, so its impact on nature. So it could also be kind of a model where an ideal volcano, and then this volcano and what it will do further. We could predict for how long it would be there, and then it would help us in preparing the logistics, and then helping humanity a better disaster preparedness. Thank you for giving a perspective that generally genetic algorithms are very slow and evolution takes into centuries. But then if you remove the time constraint and apply it to computational intelligence, it gives us a simplification of some of the algorithms. That's a very good insight you have inspired us to think about. Thank you very much.
Thanks for the question. So here I didn't go to the engineering part, but your explanation was on point. Generally, the best, as you said, genetic algorithm seems like a very slow process. Yes, very time-consuming algorithm. But if we use them in a best way, we combine these algorithms with engineering knowledge, they perform very, very well. For example, there is a one well-known case study for 1 billion variables that solve with genetic algorithm, actually evolutionary algorithm. This problem could not solve by mathematical problem even up to couple of thousand variables, and evolutionary can solve it up to 1 billion variables. So there are several ways to take advantage of these systems. And as I said, for example, if you have an unknown structure, there is no mathematical to come up with structures other than analytical methods. But genetic programming can solve it for any complex or black box or engineering problem. There are so many countless examples of how this system can be used. And I should say, if you have a problem that you can solve it very easily with engineering concept, you need to do that. But if you have a very challenging problem and you cannot solve it, evolutionary computation could be a very good alternative.
Thank you very much. And then also to a untrained professional, the relationship between a thought and then mathematical equation. It is not intuitive. And how does that connect happen? Is it like a kind of a subconscious, or there are scientific methods to plug in these variables into a big equation? I mean, like E is equal to MC square, we know one side is one variable, rest of it, as you made a big complex equation. How did you evolve? Like just that journey is something of interest for us to emulate.
So very good question. So I should say these are not analytical equations. These are empirical equations. For example, or if you embed your engineering knowledge, it could be semi-analytical equations, but they are not fully analytical. For example, these case studies here, as you can see, we want to predict the concrete creep. It is a very complex problem. There are so many. It is a dynamic and complex problem. There are so many people try to come up with semi-analytical or analytical solution for this one, with considering several variables, and we come up with the very simple equations. You can see that this is not analytical. This is fully empirical. Only these three terms, but we got a very, very good accuracy in comparison with other semi-analytical or empirical model out there. So I should say this is not like E equal to MC square, but use other concept, evolution, in order to come up with this. And in so many cases, we need these empirical equations. Yes, even in analytical, we make some simplifications, some assumption, etc. But here we purely deal with experimental data, so we can extract any information that's available.
Thank you, Professor Amir.
Sure. And if anyone else have any questions, feel free to reach me out. Or if you have a challenging problem, that feel free to reach me out for suggestion.
Certainly, Professor Amir, we'll be in touch
Sure.
with you.
Okay.
Participants, if you have any other queries, you can ask.
Queries from Naukis College students, those who joined in EduSat all. So if there are no queries, we have parallel sessions. Professor, thank you. Thanks for your wonderful speech. So we'll keep in touch with you in future conferences also. Thank you for your support.
Sure.
Sir.
Thank you, and hope you enjoy the rest of the conference, and hope see you soon. Bye-bye.
Thank you, sir.
Thank you.
So I thank all the participants for joining this session. Thank you all.
Yeah, I think Namrata, you share that feedback form. Feedback form is in the chat window. So I request for the participants to download the participation certificate of this session. Thank you all.
Thank you all.
So we have one more keynote address in the afternoon at 2 o'clock. So we'll share the link. Kindly join us. Thank you.